Okay, so another thing that we use for drawing a lot in organic chemistry with formulas and not so much with structures is curved arrows. Curved arrows are very important. They show the movement of electrons in chemical reactions we'll be talking about. We're going to be using curved arrows a lot so that we can understand how the reaction is progressing, what's happening in between each step. When we draw curved arrows, a full-headed arrow, an arrow that has a full head instead of a half head, so just to be clear, this is a full head, that is a half. Full-headed arrows imply the movement of a pair of electrons. It's very important. It means that two electrons are moving, not just one. Arrows always start at the source of the electrons and they end at what we call the sink. That's just the ending place for the electrons, the sink. So an example, you can show the dissociation of a molecule. Here's a molecule AB. You can see that the electrons in the bond itself, that's this electron and this electron. Remember, it's a pair of them. The electrons in the bond itself are moving from the bond onto element B. Element B ends up with a full-blown charge because now it has both of those electrons. And A has a positive charge because it's missing electrons. So that shows the dissociation of a molecule, its own bond breaking and moving to one of the two partners. You can also show dissociation on a larger molecule. So here's another example. This is a big branched molecule. And if you want, you can practice figuring out where all the carbons are and its formula for this based on our last discussion. But you can see here, again, this bond, both of the electrons in this bond are moving from the bond to the bromine at the end. That breaks the bond because both electrons are leaving, so we can't have a bond anymore. And that makes the bromine have a negative charge, just like above, and leaves the rest of the molecule, our branched molecule, with a positive charge. We can also have a bond break due to electron donation from another source. So instead of within the molecule, you can have electrons being donated from somewhere else that break a bond ultimately. And in this case, we actually have to use multiple curved arrows. So we're showing where the electrons are coming from, and then we're showing the bond breaking. So the bond breaking step is the same as what I just showed you, except the electrons are first being donated from somewhere else and allowing that bond to break. So we're going to have a similar action here. Here we have an oxygen donating 2 electrons, and it's donating it to this carbon atom. That's where the arrow is pointing, so it's going to the carbon atom itself. When this happens, when you have electrons being donated to a carbon atom, like this, a pair, you'll form a bond. So instead of in the opposite, when we took a pair away, now we're donating a pair and it will actually form a bond. And the carbon atom, in its now new bond it has formed, will break its set of electrons in this bond and donate it to bromine. So that's what's happening in this example. You can see another example below. This is a transfer again of electrons from an outside molecule. Here we have water, and these electrons are being given to this hydrogen in this case. So water picking up a proton, we'd call that picking up a proton. So oxygen, an electronegative element, is giving electrons to hydrogen to form a bond. And as hydrogen forms this new bond, hydrogen likes to sustain just one bond, it will break the bond between itself and bromine. So both of these electrons will then move to the bromine, making bromine negatively charged in the end. Curved arrows can also move and begin at a multiple bond position, so at a double bond or even a triple bond. But remember that the curved arrow implies that you're only moving 2 electrons in the bond. So if you are taking a double bond and moving 2 electrons, that means the sigma bond, the underlying sigma bond, stays intact while the pi electrons move. What that means is that you'll still be left with a single bond, and 2 electrons will move out of that double bond. So only one of the 2 atoms in the pi bond holds on to the pair of electrons. Here's a case where we're showing the movement of electrons from this double bond. So you can think about here are the 2 electrons that are being moved. And you can see that they are being donated to this hydrogen. That means that we are now making a bond, moving those electrons to that hydrogen. And in doing that, so again, we're forming a bond between this carbon and the hydrogen. And as it occurs, the electrons between this bond are then going to be moved to this bromine, breaking this bond. So where did that hydrogen go? You can see it was picked up right here. This is now a CH3, and we only have a single bond left because we used 2 of our hydrogens to form a bond. Excuse me, we used 2 of our electrons to form a bond to that hydrogen, making CH3, and we have a single bond left, and we dissociated the bromine. This is actually an example of a type of reaction we'll be seeing in the future. But again, just kind of follow where the arrows are going and understand what the curved arrows imply. So here's another example. In this case, the double bond is, they can act as electron sources as we showed above. This is where the double bond is the source of electrons, but they can also act as electron sinks. So this is where it is the end product, the end area for the electrons. So here, the source of electrons is this NH3. 2 of its electrons, the pair here, are being moved to this carbon. That's going to form a bond. We're taking 2 electrons and donating them, forming a bond, single bond. You can see that happens right here. And as that occurs, the electrons in this double bond are then being moved off onto this oxygen. So we're going to still get rid of that double bond. We're moving the electrons onto the oxygen. It's going to give it a negative charge, but we now only have a single bond.